Okay, so I would like to talk about some hints and solutions for the weekly problems 1.1b set. And again, this is not meant to be complete answers. It's meant to help you check to make sure that you're correct. I got a lot of feedback that students wanted some indication that they were on the right track. And so that is what this is meant to be. So the first question, when creating a multiplication table for a potential group G, what goes wrong if we try to include two different identity elements in G? When I looked at students' solutions, a lot of answers were really, really vague. What I was expecting here is like actually draw a sketch of a Cayley table and try to include two different identity elements and show what goes wrong. And then you might get some equations out of that. You will get some words out of that, but be really, really explicit about what happens. Okay, so show the reader what the connection between the Cayley table and anything else you have to say is. Exercise 2, give 2 reasons why the set of odd integers under addition is not a group. Okay, just give 2 properties of a group that the odd integers under addition does not satisfy. Okay, that one should be pretty straightforward. Prove the assertion in example 19 that this set is not a group under multiplication modulo n whenever n is not prime. Okay, so here we're supposed to show that something is not a group. And to show that something is not a group, we just need to show that it does not satisfy one of the group properties. Okay, so in this case, so remember that like the associative property is pretty much always satisfied. So we can kind of set that one aside. If something doesn't have an identity, then that one's a pretty simple one to bring up. But this group does have something that acts like an identity. It has one acts like an identity in multiplication. And then you have the idea of closure and you have the idea of inverses. And usually, or oftentimes, those are group properties that fail. So you want to show explicitly that one of those 2 properties fails when n is not prime. Okay, and so don't just like describe it vaguely, like don't just say, oh, this property fails, like give some sort of an equation that shows that it fails. Like say n is prime, so this holds, therefore, and then end your statement contradicting one of the properties of a group. Okay, and then we need to prove that something is a group under multiplication modulo 7. So there you want to show that the 4 main properties of a group do hold. And I think it's always really clear and straightforward if you just bullet point it, like, okay, 4 properties of a group, here they are, bang, 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 bang. Write them out, 1, 2, 3, 4. Question number 4, why can the same element not appear twice in any row of a Cayley table? Does this restriction apply to columns? Again, write this out similar to 1. Write a multiplication table where the same element appears twice in a row and show what goes wrong. Question number 5, complete the Cayley tables so that they form a group. Complete the Cayley tables and I don't know if you want to give some indication of like what were the key points in your constructions. You don't have to like give all of the steps, but what were the sticking points if there were any? In number 6, you need to solve the equations for x, assuming that A is a generator of C5. And for all of these, you could have a series of equations where your equal signs are lined up. So right back there with something that looks like nice algebra, like nice basic algebra with equal signs lined up where you're clearly showing the inverse. That would be a nice presentation of this question. A is a generator for C5, so you know all sorts of relations on A. And I think most students were okay with that. So I'll leave it at that. In exercise 7, which is exercise 6 in the textbook, give an example of a group G and elements A and B such that A inverse BA is not equal to B. Okay. So for this, what I would recommend, well, you know, for example, that this can't be an abelian group, because if it was abelian, you could rearrange the left-hand side of this equation and you would have A inverse AB, and then the A inverse A would cancel out, give the identity, and you'd just be left with B. And then you get B is equal to B. So you know this can't be an abelian group. So your collection of examples is pretty small, especially if you think back to the fact that this was pretty early in the course. So I would draw some Cayley diagrams. And yeah, I think a Cayley diagram would probably be particularly nice. I was going to say you could also do a multiplication table, but since this is like involving a 3-step multiplication, a Cayley diagram would show this really nicely. And use a Cayley diagram for whatever your A's and B's are, and trace your paths and show that the path corresponding to A inverse BA is not the same path, it's just B. Okay. And then the second question, does this equality hold when B is equal to A? Well, I just said that if they commute, then this is equal. So if B is equal to A, then they definitely commute. Suppose that G is a group and A and B are elements of G. Prove that for any integer n, this holds. And when I was going around in groups, when we were given this initially, a lot of people were kind of astounded when one group member would kind of write out the left-hand side by expanding it out and really thinking of the power of n means that we multiply something n times. So just writing that out, showing some of the cancellation that occurs, I think that is absolutely fine here. That's the sort of proof that we expect. Exercise 9, prove that a group G is abelian if and only if A B inverse is equal to A inverse B inverse for every pair of elements A and B inside G. The main challenge here is this is going to be a direct proof, and the main challenge here is making clear that you have shown this for every element A and B. So being careful with your definitions. From there, you're going to want to remember your socks and shoes. But yeah, just being really careful with your notation and how you're setting the problem up. And for number 10, identify the identity element and the inverse of a general element, A inside of G. G is equal to the 8th roots of unity. So in order to figure out what the identity element is, we need to remember what the operation is. So this is an example that you might have skipped over because we didn't talk a lot about it at the beginning. But remember, what is the operation on the 8th roots of unity? Well, it's like composing those 8th roots of unity, or yeah, composing the roots of unity together. Okay, so what is the identity element from that? And then you'll also get the idea of an inverse. So whether you write this down as a formula or as more of a description of what an inverse looks like, that's fine. For C, again, you want to think about what is the operation involved here. Now, if we're involving all of C, that includes 0. So automatically we can't have multiplication as our operation. The operation has to be addition. And so it's a little bit more straightforward to write down the inverse under addition than it would be to write down the inverse under multiplication. If we have a symmetry group, the identity is always going to be the do nothing action, and the inverse is always just going to be to like undo the action. It's always going to be the opposite of the action. So that's how I would describe it. And for this particular pattern, you could try to describe the exact symmetries of this pattern and then describe the inverse of each individual element. That would be great. And then finally, the set of 2x2 matrices with entries in Q and determinant 1 under matrix multiplication. Under matrix multiplication, the identity is always going to be the matrix that has ones along the main diagonal, zeros everywhere else. And you have a formula for 2x2 matrix inverses under multiplication. And you can verify that those stay inside of Q. Okay, so I hope that this was helpful. Give me some feedback on Piazza and let me know what you think of these videos, if they're helpful or if they're not. Now I feel a little bit like a social media star saying, give me a comment down below. But yeah, don't give me a thumbs up or thumbs down. That will hurt my feelings. But tell me if these are helpful. Okay, I hope it has been a little bit helpful at least, and I will make some more. Hope that you have a great day or a great night.